Welcome to Oddly Real. I'm Nem Stefanovic. Our universe is shockingly vast, with most of it in the form of enormous voids of relatively empty space between galaxies. Perhaps even more astonishing is that the universe is expanding in size, creating even more space. Even matter, which can be solid to the touch, consists of atoms which are themselves extremely spacious. An atomic nucleus contains over 99.999% of the total atomic mass, but occupies 1/10 trillionth of an atom's volume. The miniscule nucleus itself is composed of quarks, which, compared to the nucleus, are as small as the nucleus is to the atom. There is a tremendous amount of space within atoms. Yet, as seemingly empty as the universe appears from the subatomic level up to the galactic scale, paradoxically, it's not empty at all. The space within atoms is filled with force fields that permeate throughout. The intergalactic voids also contain particle matter that accounts for approximately half of all of the atoms of visible matter. Even the seemingly empty vacuum of space is teeming with zero-point energy, resulting in virtual particles that fluctuate in and out of existence. There is a real possibility that our entire universe exists as the result of a quantum fluctuation of energy from the vacuum. The concept of a vacuum, or a region of space devoid of matter, has fascinated humans for millennia. Here on Earth, a vacuum seems to possess incredible properties like the ability to adhere two objects together with tremendous strength if the space between them is devoid of air. A straw plugged at one end will keep liquids suspended within, counteracting the downward force of gravity. Additionally, there have been philosophical debates about whether nothingness, such as a vacuum, is actually something, and whether it is possible for something to arise out of nothing. In modern times, we know that the vacuum properties observed here on Earth are actually the result of the pressure of the surrounding air pressing down on the surface areas surrounding the contained vacuum. Even today, we cannot create a perfect vacuum devoid of all particles. There are always residual particles in the form of a few atoms that will remain. Outside of Earth's atmosphere, outer space is a vacuum. If we look at our solar system, the sun by itself contains 99.85% of all of the matter. Our solar system extends out to the Oort cloud, which has an outer edge that is roughly 1.5 light years from the sun. This is an enormous volume of space with very little matter distributed throughout. Our solar system is just one of over 100 billion star systems in the Milky Way galaxy, where dust and gas also pervades the space between the stars as well. Even in this vast vacuum of space, there are particles present in small amounts. There are enormous voids of empty space that exist between the galaxies of our universe that have some of the lowest densities of matter anywhere. Only 5% of the total contents of the universe are composed of ordinary visible matter. The intergalactic spaces contain, on average, 1 atom per cubic meter. This is equivalent to a density that is 1 billion billionths of the density found in the air on the surface of Earth. These particles are primarily composed of primordial hydrogen and helium atoms, but also a few heavier atoms that were expelled from galaxies at some point in the past. In total, these particles actually account for approximately half of the total atoms in the entire universe. The other half are contained in galaxies. We can measure the average temperature of a region of space within our universe. Temperature itself is a measure not of the void of space, but the kinetic energy, or energy of motion, of the particles within a region of space. The temperatures of substances in space tend to behave differently than what we're used to seeing here on Earth. Since there is very little surrounding matter in the emptiness of space, heat doesn't easily transfer away from a body into another by conduction or convection. Instead, its temperature depends more on the amount of radiation that the body receives and the rate of radiation absorption or emission of the object. Thus, matter near a star will heat up more easily. The coldest naturally occurring temperature in the universe was detected in the Boomerang Nebula in 1995. It's the result of a cloud of gas and dust that was expelled from a dying star. That cloud is expanding and hence cooling down to a temperature of 1 degree above absolute zero, which is minus 273.15 degrees Celsius. Interestingly, the actual coldest known place in the universe was found right here on Earth, where scientists in a lab produced a temperature that was just trillionths of a degree above absolute zero. One common measure of the average temperature of space uses the cosmic background radiation, or the radiation from the oldest light in the universe. This was emitted 380,000 years after the Big Bang, when the universe became transparent to light. The cosmic background radiation corresponds to a temperature of minus 270.415 degrees Celsius. Our universe is expanding, creating even more space. As the universe continues to grow in volume, this average temperature will also continue to drop. Perhaps even more surprising than the enormous vastness of space in our universe is the amount of space within matter itself. An atom is a small nucleus containing protons and neutrons surrounded by a much more expansive electron cloud. The nucleus contains over 99.999% of the total mass of the atom, but it occupies a volume that is less than 1/10 trillionth of the size of the atom. Even the nucleus itself, being composed of protons and neutrons, has even smaller component particles called quarks. The quarks are as small compared to the nucleus as the nucleus is compared to the size of the atom. Thus, atoms themselves are filled with immense volumes of space as compared to the actual mass distribution within them. Despite our picture of a universe with matter peppered across vast swaths of emptiness, it turns out that space is not as empty as it seems. If we look into the atom, we'll find that the space is permeated with force fields. For example, the nucleus is the source of electromagnetic fields, which is what gives the atoms their solidity. Even within the nucleus, the strong force dominates to keep hold over the repulsive positive charges in the nucleic structure. If we zoom out further still to look at the planets, stars, and galaxies, we also see the dominant attractive force of gravity show its presence throughout space. The gravitational field extends from all massive objects to ensnare celestial bodies into clumps of matter, planets, stars, and the galaxies themselves. There is no limit to the reach of both the electromagnetic and gravitational fields, which pervade the spaces throughout the universe. It turns out that space, or more accurately space-time, which contains all of the matter and energy in our universe, is itself an actual entity. It's not simply just an emptiness or lack of matter and energy. Instead, it is a medium that bends and distorts when in the presence of mass or energy. Specifically, the effects that we perceive as a gravitational force are actually due to the bending of space-time itself. Quantum mechanics asserts that there is a fundamental uncertainty about certain aspects of the universe. This is called the uncertainty principle. For example, we cannot know both the position and momentum of a particle to any arbitrary degree of accuracy. The more we know about a position of a particle, the less we know about its momentum, and vice versa. Interestingly, there is also a parallel to this uncertainty principle that applies to energy and time, called the time-energy uncertainty principle. There is a trade-off between the energy of a process and the length of time of that process. For example, we know that our universe is strictly governed by the conservation of energy, that energy is neither created nor destroyed, just changed in form. However, On a quantum mechanical level, nature allows for some creative accounting of that energy due to a required level of uncertainty associated with the amount of energy. For example, forces between electric charges are due to exchanges of photons between the charged particles. But the charged particles don't have extra energy to produce photons to exchange. So where does this energy come from? The time energy uncertainty principle allows for the use of energy from the vacuum so long as its time duration is within the bounds of the uncertainty threshold. If the energy is large, it can only exist for a short period of time. Alternatively, longer range electrical interactions are possible, requiring more time, but only if the energy is less. In fact, it's this time energy uncertainty that explains the diminishing strength of an electrical force over distance between electric charges. We call these ephemeral particles that appear and disappear from the vacuum virtual particles. Their existence is possible because of the requirement for a certain degree of uncertainty between energy and time. Rest assured, though, that when we conduct a measurement to measure the energy of a system overall, it will adhere to the universal law of the conservation of energy. Another way to think about virtual particles is to ask the question, what happens if you remove all matter from a region of space? There actually couldn't be zero energy, since this would violate the uncertainty principle. There must always be a minimum amount of energy, which we call the 0 point energy. Even empty space contains energy, making it not so empty after all. There are significant implications to the existence of virtual particles within the vacuum. The vacuum is filled with these particles that appear and disappear at random, which we call vacuum fluctuations. Virtual particles can take the form of any kind of particle. If the particles are very massive, it means that they would only exist for a very brief period of time. For example, an electron and positron pair can be spontaneously created, but would last for less than 10 to the power of minus 21 seconds in time. For some comparison, this is the time it takes light to travel 1/1000th of the distance across a hydrogen atom. An individual charge in space is surrounded by clouds of such virtual particles. The charged particles interact with virtual particles, resulting in changes to the strength of the electrical forces between the charged particles. These modifications to the electromagnetic forces are calculable. Measurements by CERN have shown that if charges approach each other to a distance of 100 millionths of the radius of a hydrogen atom, or 1,000 times smaller than a nucleus, the electromagnetic forces appear 10% stronger. Our normal interactions with the electromagnetic forces, like electrostatic charges on clothing, or even at the atomic scale, are the result of the electromagnetic force interacting with virtual particles to reduce the strength of the forces. Experiments match calculated predictions to at least 1 part in 100 billion, making them extremely accurate. There is a way to both test the presence of vacuum energy and even extract a little bit of useful work from it through something called the Casimir Effect. Two parallel metal plates that are close to each other, but separated, only allow certain 0 point waves of energy to exist between them. Only waves with an exact integer number of wavelengths can fit between the plates. This number is fewer than the waves that can exist in an open vacuum. As a result, there are more energies and virtual particles that can exist outside of the two metal plates than within. There is essentially less pressure in between the plates. This produces an attractive force between the plates. Note that the force produced is very small, but the converging plates can in principle be used to produce useful work. However, once the plates are together, the system would need to be reset by putting energy back into the system to separate the plates. It's not a very practical way to generate useful energy. There is also a real possibility that the entire universe is a result of a quantum fluctuation from vacuum energy. In order to explain this, we need to understand how gravitational potential energy can be thought of as a kind of negative energy. When an object with mass is far away from a gravitational body, we can say that the gravitational potential energy of the object is zero. This makes sense since an object on its own in outer space, away from others, can be thought of as not possessing any additional energy. However, when the object is pulled in closer toward a larger, more massive object, its potential energy is now reduced, making it less than zero. The potential energy must be less since part of that energy was converted into a kinetic energy of motion to bring it closer to the more massive object. In our universe, there are many objects that have negative potential energy, similar to this example. If we treat their energies as negative and sum the rest of the energy in the universe, including accounting for all mass energy according to E equals mc squared, then it's possible the negative and positive energy amounts sum to a value that is very small, close to zero. The time energy uncertainty principle would then technically allow this small amount of energy to exist for a very long amount of time, hence the existence of our universe. This is a very interesting concept, but it is far from a proven or even accepted theory. I hope you enjoyed this episode, and remember, oddly real, really interesting.